So the topic of my talk will be the large coupling strength limits, both in DFT and Hartree-Fock adiabatic connections. So let me start by, it's not working, yeah. Okay, so let me start just by defining the notation to be sure we are all on the same page. So as you saw, I come from a chemistry department, so we address the many electron Hamiltonian in the Born-Oppenheimer approximation. So I will use this notation T for kinetic energy of the electrons, VE for the electron-electron interaction, and for the one body external potential, either V external or VNE. Typically, we're interested in cases where the external potential is due to the nuclei, and what we want is the lowest eigenvalue of this Hamiltonian, of course, with the fermionic antisymmetry as a function of the positions of the nuclei. And I will focus on this talk on both Kohn-Sham DFT and Hartree-Fock. I guess everyone is well aware of those theories, but I have them here in one line. So in Kohn-Sham DFT, essentially what we do, we minimize, so we can in principle access the exact ground state energy of the many electron Hamiltonian by minimizing overall Slater determinants, the one body part of the Hamiltonian plus a Hartree exchange correlation functional that depends on this Slater determinant only through the density, and the density is just the marginal of the square of the wave function. While in Hartree-Fock theory, okay, we never access the exact energy, we access the so-called Hartree-Fock, we never access the exact many body energy, but the Hartree-Fock energy, which is the minimum overall possible Slater determinant of the true Hamiltonian. And in both theories, both Kohn-Sham and DFT, both Kohn-Sham and Hartree-Fock, the correlation energy is defined as the difference between the true ground state energy and the expectation on the Slater determinant, whether the Kohn-Sham one or the Hartree-Fock. And the topic of my talk will be these so-called adiabatic connections. So these are ways essentially to define formulas for the exact correlation energies, formulas that we use then to make approximations. So in density functional theory, typically what we do, we turn on and off the electron-electron interaction by multiplying it by a real parameter lambda. And then what we like to do is to keep the one electron density fixed by means of a Lagrange multiplier, which will be a one body potential, which will also depend on lambda. And then by looking at this expectation value, so the expectation of the electron-electron interaction on the wave function psi lambda that minimizes this Hamiltonian, minus the one on the Slater determinant, on the Kohn-Sham Slater determinant, you can easily find this exact formula for the correlation energy. And this is essentially a trick to recover from the electron-electron expectation the correction to the kinetic energy. Now, at small coupling strength, you have a perturbation theory that in Kohn-Sham theory is the so-called Gerling-Levy perturbation theory. And then the focus, one part of my talk will focus on this large lambda limit. So this is what I mean by strong coupling. And I also look at Hartree-Fock theory, and I will later explain why I look at both theories. So in Hartree-Fock, instead, what we turn on and off with the real parameter lambda, it's the so-called fluctuation potential, which is the difference between the true electron-electron interaction and the Hartree-Fock potential, so the one body operator that arises when we minimize the Hartree-Fock energy with respect to the orbitals, which is made of the Coulomb or Hartree part and an exchange part. But it's lambda independent. So you do your Hartree-Fock calculations once for all, and then you add this fluctuation potential multiplied by a parameter lambda. And in this case, the one electron density will change, going from Hartree-Fock to the true one. And if you go beyond one, it will change accordingly. And in this case, you define this expectation value. So you consider this wave function psi lambda that minimizes this Hamiltonian here. And you look at the expectation value of the fluctuation potential on psi lambda minus the one on the Hartree-Fock determinant, and you have a very similar expression for the Hartree-Fock correlation energy, just that now this object is defined differently. Now, at small coupling strength, again, you have a perturbation theory, which is the so-called Møller-Plesset perturbation theory. And it's, let's say, much easier to compute than Gerlin-Levy. So Gerlin-Levy typically has been computed only up to second order, that I know, at least for chemical systems. Møller-Plesset, at least for small systems, people have computed several orders. And then I will consider in this talk also what happens at strong coupling, also in Hartree-Fock theory. Okay, so just to visualize this kind of integrand that we have both in Hartree-Fock and DFT, okay, will depend on the yes, the lambda, this coupling strength. A small lambda, you have perturbation theory. We look at this large lambda limit, and then you get from this integral the correlation energy. So the focus of my talk, as said, will be these two limits and their use to make to build approximations. So if you want to see it from the point of view of model reduction, the model reduction part is okay, stays in the fact that these two limits are much easier to compute and to study than the lambda one, which is the difficult one, the physical one. So the idea is to gain information to make approximations. Now let me mention that this leading term here in the DFT part, here SE stands for strictly correlated electrons, was illustrated in a very nice way by Gero Frieseke 2 weeks ago in the other workshop. So I strongly advise to watch this video if you haven't done it. Okay, so one can ask exactly why looking at this large coupling strength limit. So for the DFT part, what I find very interesting is the fact that, okay, in DFT, we have a way to define, to construct approximations for the so-called exchange correlation energy, so the part that we don't know how to approximate. And they are based by a common strategy, which is looking at the local density gradients, the so-called local Kohn-Sham kinetic energy, exchange, and then the unoccupied Kohn-Sham orbitals. But of course, no one tells us that this is the right way to go. This is, let's say, the traditional way in which approximations are built. The nice thing of looking at this strong coupling limit in DFT is that it provides a very well-defined asymptotic limit for the exact exchange correlation functional. And what we see in this limit is that none of these, so these ingredients do not appear at all. And actually, the functional is built from constrained integrals of the density. And this is a review we wrote recently also with Gero and Augusto Gerolin. So okay, everything is explained there. The other part that will be mainly the focus of this talk, actually, it's both for DFT and Hartree-Fock, the idea, which is actually quite an old idea, it's even dates back to Wigner, who used it for the uniform electron gas, is to build approximations for the correlation energy by interpolating between small and large lambda. So it will be, of course, an uncontrolled approximations because it will depend on the function you choose to interpolate between these two limits, but DFT is all about approximation, so somehow, somewhere you have to make choices and approximations. And so this is something I will focus on. And of course, this kind of interpolation, you can do it both on the integrated quantities, but you can do it also locally in each point of space. Okay, so let me quickly review the DFT one, which, as said, partly was treated by Gero Frieseke, and then I want to focus more on maybe the Hartree-Fock. Okay, so for the DFT, we know nowadays a lot. So we know that at large lambda, this so-called adiabatic connection integrand here that I defined earlier, has this kind of expansion where, okay, this is the leading term, and then we have a sort of 0-point oscillations, and we also know that the next term will be of this sort, and then there will be this kind of exponential terms that will distinguish, for instance, between fermions and bosons or between different spin states. And this leading term here, yeah, as said, it's an asymptotics for the exact exchange correlation functional, and by uniform coordinate scaling, you can show that the exact limit when we go to when we drive the system to low density. And these two functionals are highly non-local. So let me just quickly review for the people who have not seen the talk of Gero Frieseke. So very quickly, the physics behind, and then for the math, I refer to the talk of Gero or our recent review. So the math, the physics, the physical intuition is quite simple. The idea is that when you go to this limit, you end up minimizing only the electron-electron repulsion among all wave functions with the prescribed density. And then you're minimizing wave function collapse, so will be zero everywhere except on a very low dimensional portion of your configuration space, which is parameterized by these so-called commotion functions, or the Monge maps of optimal transport, in which you can distribute one electron according to the density, but then the other positions will be determined by these maps, which satisfy group properties for the indistinguishability of the electrons. And they will also satisfy this kind of, people will recognize push forward condition from optimal transport, but physically what it means is that the probability of finding one electron somewhere at position R, the volume element dr, must be the same of finding the other electrons in this so-called strictly correlated position. And here is an example. In a density which is high density on the lighter regions, you will have a kind of, it's essentially a crystal in a metric. Okay, the nice thing is that if you can determine these maps, and this is a big if, how easy or how difficult it is to compute them is actually quite difficult, except in some simpler cases. You have not only the functional, but also the functional derivative, which has a very simple physical and transparent physical meanings, because it's just telling you that if you are at position R, you know where the other n-1 electrons are located. And so you can compute the net repulsion that you feel from the other n-1 electrons, and the one body potential that exerts exactly that same force is the functional derivative. This is something that can be shown rigorously. It's also a result from optimal transport. But essentially what is interesting is that the Hartree exchange correlation potential of Kohn-Sham theory tends to this potential in the low density limit. So it's a nice physical limit for this potential. And this also illustrates the next leading term in the large lambda limit, because, okay, if this potential exactly represents the net force that an electron feels when it's a position R, if you reverse the sign, it compensates exactly the force. So here, this V infinity is the same potential with reversed sign. So you can create a classical potential energy which has a degenerate minimum on the manifold parameterized by these maps or commotion functions. So this is a simple example for two electrons in 1D. You have a potential energy that it's degenerate on the manifold of these so-called optimal maps. And then the conjecture for the next leading term, a conjecture we did in 2009 in this paper, is that this term, the next term, is simply given by 0-point oscillations around this manifold in the direction orthogonal to the manifold. And then you get this kind of expression in which you have the trace of the square root of the Hessian of this potential energy surface on the manifold. And now, so this is an old result. What is nice is that more recently this was proven rigorously, at least for the n electrons one-dimensional case by Maria Colombo, Simone Di Marino, and Federico Stra in this paper. So there are also some rigorous results on this next term. Okay, now chemical systems, unfortunately for me, because I like this limit very much, are far from this low density limit, but something we looked at to see how it would work if we use it in Kohn-Sham are systems that are driven to the low density limit. So for example, our quantum Monte Carlo friends, they studied this kind of system. So electrons confined in 2 dimensions and then with an harmonic, so in 2D, 2 dimension, and then with an harmonic confinements. And these are systems that can mimic electrons at the confined at the interface of semiconductor heterostructures. And then you have lateral confinement with the lithographic techniques, but here is just 2-dimensional electrons in the harmonic potential. And what you have is this transition from, let's say, a Fermi liquid structure in which the density is determined by essentially the orbitals you occupy in a 2-dimensional harmonic oscillator, a bit more, let's say, a bit fatter because of the interaction, but qualitatively that's the structure. A very low density, you go to this sort of Wigner rings. And these very low density Wigner rings are essentially impossible to describe typically with the Kohn-Sham, with the usual approximations. What was nice that what we did was to implement Kohn-Sham with this strictly correlated electron functional that for spherically symmetric system is easy to compute, doing self-consistent Kohn-Sham. And then what we saw is that you can really go from high density where essentially you have this Fermi liquid-like structure to this Wigner rings. So indeed, this is not surprising because we know this asymptotically is the exact functional, and then yeah, we are very close to the limit in which this functional is exact at low density, but still it's nice to see that Kohn-Sham can do also extreme correlation if you use the correct functional. And also what you saw here in blue, it's the self-consistent total potential, so including the Hartree exchange correlation from the SCE plus the harmonic. Then you see that at high density, when the system is weakly correlated, this is the density, the red curve, and this is the Fermi level. So you have the Fermi level, it's always above your potential, while in the low density case, the strongly correlated case, the self-consistently, the strictly correlated electron potential creates classically forbidden regions inside your system. So this is the highest occupied level. So these classically forbidden regions in the Kohn-Sham potential are known to be, seems to be really the key to describe, let's say, strong correlation with Kohn-Sham. And this has been observed also, for instance, in stretched bonds, that a similar change in the nodal, in the classically allowed forbidden regions, it's there. I mean, the classical turning point are changed. And it's also accurate. So this is yes, comparison with the quantum Monte Carlo results at very low density. So the red is the quantum Monte Carlo density, and the blue is this self-consistent Kohn-Sham SE. Okay, now this is nice. It's easy in a way because everything is at low density, so you can use nicely this functional. However, chemistry is much more challenging because you have to describe at the same time the let's say, weak correlation around the atoms with the so-called strong correlation or static correlation if you start to stretch bond, or the physics of entanglement. And this is where the challenge is. So for example, this is the H2 molecule, the full CI, and this is our results. What happens if you use Kohn-Sham with this SE? It's very bad, except when you stretch the molecule, because then you have this physics of too far electrons very correlated, and then it's fine. But of course, here it's a very big error. So one thing that we tried to do is, and this was an idea of Stefan Vučković, was to use the mathematical structure that we observed in this limit. So the kind of ingredients that we have observed that are different from the traditional ones, to try to build new approximations. And for example, this orange one was obtained by tickling a bit with this kind of ingredients, but it's still a challenge to have uniform accuracy, exactly because of this balance of weak and strong correlations. Okay, so now so there is a lot that has been done, not only by us, but by other people like also Matthias Enser's group and so on. What I would like to focus here is this idea of this global interpolation. So interpolating between small and large coupling strength to build approximations. So the first thing is that aside this strong coupling limit, it's quite difficult to compute. So Gero gave a very nice overview of the different methods. So what we have to do first is to make approximations for it. So they exist already several different approximations, sort of local density, which would be Wigner crystal if you want, a gradient expansion, the so-called point charge plus continuous model that was built by Mike Seidel and co-workers. And then there are some models that keep these integrals of the densities, but more recently, we actually, Simon Šmiga, in this paper, he has built a very accurate generalized gradient approximation for this limit. Here S is the reduced density gradient. And so it's a kind of this kind of approximations. And what is nice of this so-called harmonic PC model, so he has done it both for the leading term and for the 0-point oscillations. It seems to work to reproduce quite accurately the exact strictly correlated electron results that we could do for at least for small atoms. But what is nice is that also the functional derivative seems to agree quite well with the exact one, the strictly correlated electron one, so which is the blue, and this is this yellow is this new GGA approximation by Simon Šmiga. So what is nice is that with this new kind of approximation and with the technique that Simon has developed to optimize effective potential techniques, he could do self-consistent calculations with this kind of functionals built by interpolating between second order perturbation theory and this large lambda limit approximated with this generalized gradient approximations. And the only thing I would like to show is this correlation potential of Kohn-Sham for neon and for the CO molecule. And what we see is that this potential have a very decent shape. I mean, for people coming from DFT, they know that typical DFT approximations, if you look at the correlation potential, has nothing to do with the reference one or the let's say, accurate ones. And here instead we see some very good agreement. So this in blue is the reference. In green is if you use only second order perturbation theory, and then the red and the black are two different interpolation formulas. The red uses only the leading term, so it really interpolates just between this line and this line. The black uses also the second order term, so it has also this correct 1 over square root lambda. So we also see that adding this second term always improves the results. So this, in a way, it's nice. Now, what's a bit puzzling for us was the fact that okay, the results are not so accurate, so I will not show them. I mean, they are promising, but it's clearly there is still a lot to do if we look at energies. Instead, something that was noted already some years ago particularly by Eduardo Fabiano, was the fact that, quite surprisingly for us, if you look at non-covalent complexes, so systems, cross-shell systems that are bound by non-covalent interactions. Quite surprisingly, if you take these same interpolation formulas with this same gradient expansion or GGAs for the large coupling functionals, you get a very good result if you just take the Hartree-Fock orbitals and the Hartree-Fock density and you put in the formulas. So you take the MP2 energy, second order, the MP2 correlation energy for second order, and you take this, the Hartree-Fock density. And here is an example so you see here the reference. And here the one of these interpolation formulas done with Hartree-Fock. Just for comparison, you see how bad can it be if you use instead the Kohn-Sham. So that's why I didn't want to show too much of this with Kohn-Sham. Okay, so because of this, and this was a bit frustrating because we had a whole theory for Kohn-Sham DFT, and then it turned out to work instead with Hartree-Fock, which of course, okay, maybe it's not so. There is a lot of literature in using Hartree-Fock inside DFT functionals, but here we kind of, okay, we really had a whole theory of interpolation, etc. So this is what actually motivated us to look at the Hartree-Fock adiabatic connection, because the idea was, okay, if this works so well, why can't we even improve it if we study this kind of adiabatic connection, this kind of strong coupling limit, and then have directly a theory designed to give you the Hartree-Fock correlation energy, so without having to do any self-consistent cycle, plus designed to work with the MP2, so that or with the MP. So it looked like much more promising to do something like this, but I admit it was purely motivated by this observation that it worked so well. Okay, so that's what we did next. So we took this kind of adiabatic connection. And so just to remind you, we have here the electron-electron repulsion. This operator J is nothing else than the Hartree potential of the Hartree-Fock density. And the operator K, it's the typically exchange, it's the exchange operator with the kernel, with its usual kernel. Okay, and these are the formulas I had before. This is an adiabatic connection that has been studied a lot in quantum chemistry because it's used to study the radius of convergence of Møller-Plesset perturbation theory. There is a very nice review here by Antoine-Marie, Hugh Barton, and Pierre-François Loos on everything that has been done on this adiabatic connection. However, okay, no one was crazy enough to look at the lambda infinity limit, which is what we have done. Okay, so how does it work in this case, the large coupling strength limit? So in this case, what we did, we started with a very simple system, the hydrogen atom. You can think it's crazy because Hartree-Fock is exact for 1 electron, but first of all, because you have this exchange operator, you can look at different spin states. So you can have, for instance, half spin up and half spin down, and then Hartree-Fock is not at all exact. It actually gives you exactly the error you make if you dissociate the H2 molecule in a restricted framework. But it's also interesting, by itself, because it's essentially almost exactly soluble. So it's going to tell us a lot, and I will show that these results can be generalized to the many electron case. So the kind of Hamiltonian we have here is very simple. There is no electron-electron interaction. The exchange operator is just multiplied by this parameter S, which reflects the spin states essentially of your system. So you fix your Hartree-Fock orbital once for all, your initial calculation. Your J is the Hartree potential. Then it's easy to see what happens when lambda is very large. Here you have a minus. So essentially, when lambda is very large, your electron ends up localizing in the minimum of minus the Hartree potential, which in this case looks like this, and the minimum will be at the nucleus. you can show that the exchange operator will enter at the same order of the kinetic energy. So it will be next order. So what happens is, without the exchange operator, you would expect 0-point oscillations around this well. Because there is the exchange operator, what happens is that all what it does, it mixes in some excited states of the, let's say, if you make here an harmonic approximations, it will mix in some excited states. And actually, for the S equal 1 case, we even have an analytic solution. So the final solution is exactly a linear combination of the ground and first excited state. So essentially what happens to the minimizing wave function here, the wave function that minimizes this Hamiltonian, is simply that at very large lambda, you have a scaled variable that is important, and then in the lambda infinity limit, your wave function tends to a delta function around this point. And the representation of the delta function is this function here with a node, the blue one, which I said for S equal 1 is just the exact linear combination of ground and first excited state. And for the case S equal 1/2 here, for a half spin up and spin down, you don't have an analytic solution, but you have this red curve, which is very similar, and you can easily find it by expanding on the harmonic oscillator states, and it converges very fast, but it's not a closed form solution. So once you have this, you can easily find the expansion. So what you have is that the leading term is simply the electrostatic energy of this point charge here. The next term, this 1 over square root lambda, is this kind of enhanced 0-point oscillation, which determines this eigenvalue here. And then you also have this lambda 3/4 term, which does not appear in the DFT case. And it's there simply because in this case, your electron is localizing on the nucleus. So the divergence or the non-analyticity of the Coulomb potential at the nucleus, together with the cusp in the Hartree-Fock orbitals, make this 1 over lambda 3/4, which is not there in DFT, because in DFT you have the density constraint, so the configuration with 1 electron at the nucleus will have negligible weight. Now you can use this result to go to the many electron closed shell case. Closed shell because otherwise I need to decide what to do with my spin, so let me stay in the closed shell. So what happens, you can easily write, so what happens is very easy to prove in the physicist sense, that if you write an ansatz for your wave function as a Hartree product of localized orbitals, what you can show is that the leading term here will be simply determined by this functional of the Hartree-Fock density. I call it EL for E electrostatic. And what this functional is, it's simply the energy of a crystal. I mean, it's a crystal of point charges. So the electrons become, and they are bound by a sort of positive background given by the Hartree-Fock density. So essentially in this, so the lambda infinity limit of the adiabatic connection that has a small, as weak interaction expansion, the Møller-Plesset perturbation theory has as a large lambda limit, large coupling strength limit, a crystal bound by a sort of positive charge given by the Hartree-Fock density. So this results, okay, we like it very much because it's telling you that also in this case, it was good to make approximations in terms of the Hartree-Fock density. So this is really an electrostatic functional, which is even not that complicated, of the Hartree-Fock density. And then if you take, so for instance, for 2 electrons, like the helium atom, you would have this kind of situation. And then by putting localized orbitals around these minimizing positions as ansatz for your wave function, if you optimize the shape of these localized orbitals,
what you find is exactly back the solution for the hydrogen atom with S1/2. So this red, so this red shape here. Okay, so this is the best spherical orbital, localized orbital you can put in your Hartree product. So this allows you to get a variational expression for your next leading term, and also for this 3/4 term, because each time one of these minimizing positions happens to be at a nucleus, you have exactly the same mathematics for the hydrogen atom. So you also have an expression in which you have to consider only minimizing positions that happens to be at the nucleus. So in this case, you will not have this term. But for instance, for the lithium atom with 3 electrons, you will have 1 electron at the nucleus, this calculation, and 2 around, and then you will have this, this kind of term appearing. Okay, and this is the paper. It was a team effort, and the main author Tim Das is a very excellent PhD student in our group. He will be ready in 1 year, so watch, no, 1.5 years, so watch for him. And of course, at the end, we don't want to do this electrostatic minimization each time. So what we will do again is to use gradient expansion or generalized gradient expansions for these functionals. Okay, just very quickly, I like to mention simple inequality. So this electrostatic functional, you can show, but that's quite easy to see. That will be always a lower bound for the DFT one, so the strictly correlated electron one. So for a given density, you always have this lower bound, and only for a uniform density, these two functionals will be equal. And then if you try to do a second order gradient expansion, the gradient coefficient will have opposite sign. It will be positive for the DFT and negative in this case. Okay, what we have done now with this was to, since we had observed that for non-covalent interaction it could work well, what we tried to do is to use this interpolation idea to see if we could correct the MP2 errors for large non-covalent complexes. So there was recently this quite nice paper from Philip Furken and his co-workers, and they showed that the MP2 has an error that increases with the system size. So this is a set of 7 molecules, which they have shown this, and we will consider this kind of systems to see if we can correct MP2. So what we have done is to try 2 different interpolation formulas, which were really tailored to this, let's say, adiabatic connection in Hartree-Fock. So they also, so here I'm always drawing it as convex, but actually the Hartree-Fock adiabatic connection can be first concave and then convex. So this kind of form, they can also get this concave convex behavior. And here, okay, instead of parameterizing V lambda, we just interpolating its integral such that we don't even need to do an integral. We just have to set the lambda 1 here. But this kind of form, for example, is designed to also have this lambda 3/4 term at large lambda. And then we had some GGA or GA, in this case, approximations for the these lambda infinity functionals that are also based on the comparison with the DFT ones. What we did was then to, okay, we had some empirical parameters, I have to admit it. So we had the 4 parameters in this case and 2 in this second case. And we fixed the parameters to a set of 22 non-covalent complexes, which are much smaller than the one we want to address. So the idea is we fit our this kind of models to a smaller set and see if it can then correct larger models, if it generalizes. So one thing I should have mentioned already before, that, of course, this idea of interpolating between the 2 limits is quite old. In the DFT context, was proposed by Seidel, Perdue, and Levy, which is why I have this SPL form name in the form.
But the idea was abandoned because of the lack of size consistency, which you can imagine because you have integrated quantities that will appear in a nonlinear way. However, we had seen that you can very, very easily compute accurate interaction energies by correcting at zero extra computational cost this size consistency error. This was really an idea of Stefan Vučković. And the idea is quite simple. So for instance, consider this very simple model to interpolate between this limit and this limit. So by setting the parameter b to the ratio between these two functionals, you are assured to get the two limits right. Now this model, it's simple to see that it's size extensive because if I have n times the same system, I will get an n here in front for this functional, and here in the ratio, the n will disappear. So it is automatically size extensive. However, it's clearly not size consistent because when the two systems A and B are different, here the parameter B will not scale. So I will have, this limit will be different than the sum of the two. However, the question we should ask is whether which is what we are interested in, is whether the potential energy surface has a good shape or not. So what I mean is, okay, if I change the distance between these two systems, does this energy change with the good shape or not? And essentially what you have is that if you go to infinite distance, it's very easy to compute the asymptotics because you just have to put inside the nonlinear form the sum of the ingredients instead of having a sum of nonlinear form applied separately to the two systems. So here is an example. If you compute your interaction energy with respect to these asymptotics, you are very far from the correct result. But if instead you compute your interaction energy with respect to this limit, which is very easy to compute, then you realize that your shape is actually not quite bad, actually it's quite good. So that's the whole trick, is very simple. And it's the paper. Okay, so we applied it to a set of systems, and then I will quickly come to conclusions. So this is the part we fit. These are some data sets, Nobel gas dimers, charge transfer complexes, dipole interactions. S66 is a larger set, and then this L7 was this set of large molecules. And here we have set to 1 the MP2 error, so you can see how much we reduce MP2. The MP2 error. So it's, especially for this L7, it's a very good reduction. This is a comparison with, for instance, Bitrilip D3, and what you see is that we can do quite better for this L7, but we can also do much better for charge transfer complexes. So we can do quite good overall this different kind of non-covalent interactions. Okay, this is another plot that is not interesting. And maybe the last thing I would like to show is that it's not a one-directional correction. These are some potential energy surface, and what you see is that, so the black is the reference, that for instance SPL2, which is one of the two, the one that works best of our interpolation formulas, it's able to correct MP2 both when it underbinds, but also when it overbinds. So it's not correcting always in one direction, and this is because this change from concave to convex behavior that we have allowed. And the other point is, for a charge transfer complex, we are doing very well, while for instance, what people have observed is that some of the functionals, if you add the dispersion correction, they worsen. So you see this for, this is a double hybrid that would have the same cost as our functional. And when you add this dispersion correction, it actually gets worse. So we are able to do this non-covalent interactions without any dispersion corrections. Of course, this is also a good point. Okay, I don't have any conclusions because I find conclusions always boring, sorry. Instead, I would like to thank the people who really have done all the work, particularly Team Das, okay, Derkoy, Mike Seidel, of course, who is the main mind behind this strictly correlated electron limit class, Simon Smiga, Stefan Vučković, Julian Sara for some of the first part, our collaborators in Lecce, and former collaborators who also contributed. And then I thank you for your attention.